Hi future engineer! Today, we will talk about thermodynamic cycles. There are 6 cycles to be discussed in total, so make sure to check them all. And they are as follows: Carnot cycle, Otto cycle, Diesel cycle, Dual cycle, Stirling cycle, and Ericsson cycle. But for today's video, the discussion is all about Stirling cycle. I also invited my 2 colleagues to help me with the discussion. So don't be lazy and grab your scientific calculator. So if you're ready, let's begin. The genius man behind the Stirling cycle is Robert Stirling. He is a Scottish clergyman, best known as the inventor of the Stirling engine, which is a type of external combustion engine. Stirling's first patent was granted in 1816 for what became known as the Stirling Cycle engine. His company manufactured engines from 1818 to 1922, during which time they were used to pump water on farms and to generate electricity. Later attempts to develop the Stirling engine for commercial use proved largely unsuccessful, though its potential for quiet operation, multiple fuel sources, high efficiency, low pollution, and high power density continues to hold considerable attractions for researchers. For a short trivia, did you know that Stirling cycle has an efficiency equal to Carnot cycle? Because the efficiency of the Stirling cycle is little less than the efficiency of the Carnot cycle efficiency. But the Stirling cycle is considered to have the same efficiency as the Carnot cycle if all the process is completely reversible. And that's it. Moving on to the PV and TS diagram, or the pressure volume diagram and temperature entropy diagram. The idealized Stirling cycle consists of 4 thermodynamic processes. The first process, from point 1 to 2, is an isothermal heat addition process, wherein heat enters at constant temperature from an external source. This will result with an increase in volume or expansion of the gas. There will be a dramatically decrease of pressure at this process. The second process is an isometric process, or isochoric in other books and other sources. But let's just use isometric to avoid confusion. From point 2 to 3, after the volume of the gas has been increased, it will remain constant. Heat removal in the gas is offered at this point in preparation for the third process. Again, the pressure will decrease but not as large on the first process. The third process, from point 3 to 4, is an isothermal process again, but this process involves heat rejection. Like the first process, the temperature is constant and the heat removed will be transferred into the regenerator. The pressure will start to increase from this point. Lastly, the last process is called isometric process. From point 4 to 1, the volume will be maintained at a constant value. Then, the pressure will increase more than the other. Then, the heat will be prepared to enter again to perform the cycle. Therefore, the cycle is now performed. Alright, unfortunately, time is up for me. But here's my colleague Jackie to discuss the Stirling cycle's formula and its derivations.
Thank you, Ace. So now, let's proceed to the discussion of Stirling cycle's formula and its derivations. The first process from point 1 to 2 is isothermal heat addition process. So we can say that T1 is equals to T2. In this case, we can use the combined gas law, which is P1V1 over T1 is equals to P2V2 over T2. Since temperature is constant, we can exclude the temperatures from the formula. So it will become P1V1 is equals to P2V2. For the heat added, the general equation of heat is Q equals to delta U plus Wn. Since the temperature at point 1 to 2 is constant, so the delta T is equal to 0. Therefore, the general equation of heat will be QA is equals to WN. Leading us to WN is equals to the integral of PdV. Then take note that PV is equals to C or P is equals to C over V. So, we substitute the P to the equation. So, we can say that WN is equals to the integral of C over V dV. Then simplify and it will become WN is equals to C multiplied by V2 minus V1. Then apply the rule of logarithm. So, WN is equals to C ln of V2 over V1. Then transform your C into PV again and WN with QA. So, QA is equals to PV ln of V2 over V1. And since PV is equals to MRT, we can also say that QA is equals to MRT ln of V2 over V1. Process 2 to 3 is an isometric or isochoric process. Since it is a constant volume process, so V2 is equals to V3. Using again the combined gas law, which is P2V2 over T2 is equals to P3V3 over T3. Then exclude the volume from the formula since it is constant. So it will become P2 over T2 is equals to P3 over T3. Process 4 to 1 is isometric process, same as process 2 to 3. So, V4 is equals to V1. We still derive the formula from the combined gas law, which is P4V4 over T4 is equals to P1V1 over T1. Exclude the volume from the formula and it will become P4 over T4 is equals to P1 over T1. The process 3 to 4 is also an isothermal process like process 1 to 2, but this process involves heat rejection. Since it is an isothermal process, the temperature is constant, so we can say that T3 is equals to T4. Combined gas law will be used again for these points, so P3V3 over T3 is equals to P4V4 over T4. Then, excluding the temperature from the formula, it will become P3V3 is equals to P4V4. For the heat rejected, from the general equation of heat, which is QR is equals to delta U plus WN. The process of deriving QR is the same with the process of deriving QA, although we replace the maxima and minima values of the integration with 4 and 3 instead of 2 in 1, since the removal of heat occurs between points 3 to 4. Thus, this will give us a formula for heat, which is QR is equals to MRT called ln of V3 over V4, or QR is equals to PV ln of V3 over V4. For the cycle performances of Stirling cycle, the first one is the network of the cycle. Network of the cycle is equal to the heat added diminished by the heat rejected. So, W net is equals to QA minus QR. Next is the mean effective pressure. Mean effective pressure is equal to the work net all over volume displacement. So, MEP is equals to W net over VD equals to W net over V1 minus V2. Volume displacement is equal to the maximum volume minus the minimum volume. Last but not the least is the cycle thermal efficiency. Cycle thermal efficiency is equal to work net over heat added. So, EC is equals to W net over QA. We can still break down EC, right? So we can say that EC is equals to QA minus QR over QA. Then simplify. EC is equals to 1 minus QR over QA. Then substitute the formulas of QR and QA. And we will come up to EC is equals to 1 minus MRT cold ln of V3 over V4 over MRT hot ln of V2 over V1. Since V4 is equals to V1 and V2 is equals to V3, then V3 over V4 is equals to V2 over V1. So, EC is equals to 1 minus MRT cold over MRT hot, or EC is equals to 1 minus T cold over T hot. And that's it. Let's move on and apply the discussed formulas to an example problem. Here's my colleague Joshua to help you with that.
Thanks, Jackie. Now, as Jackie said earlier, we will now head on for the example problem. The best part, right? Now, grab a sheet of paper and calculator, the scientific one, of course, and let's get this done. An ideal Stirling cycle running on a closed system has an air at 200 kPa, 300 Kelvin at the beginning of the isothermal compression process. Heat supplied from a source of 1700 Kelvin is 800 kilojoules per Kelvin. Determine the cycle points, performances, and the mean effective pressure. Okay, so we need to compute the cycle points, the cycle performances, and the MEP. Let's elaborate the given to help us what we are going to solve first. Now, for P3, we have 200 kilopascal, T3 is equals to 300 Kelvin, T1 is equals to 1700 Kelvin, and QA is equals to 800 kilojoules per kilogram. Those are the given. Solutions. For compression ratio, or the RK, first we have QA is equals to RT hot ln of V2 over V1. R is always constant. Now, take note that RK is equals to V2 over V1 and RK is also equals to V3 over V4. Now, 800 kilojoules per kilogram is equals to 0.287 kilojoules over kilogram per Kelvin times 1700 Kelvin ln of RK. Now, evaluate. The answer is RK is 5.154. Next is cycle thermal efficiency, or the EC, but not EC though. EC is equals to 1 minus T cold over T hot. Now, substitute 1 minus 300 over 1700 Kelvin. The answer is 0.8235, or multiply it by 100%, it will be 82.35%. The next is for heat rejected, or the QR, we're going to use EC again. EC is equals to 1 minus QR over QA, right? We have EC and QA. So, we substitute CC and QA. Now, 0.8235 is equals to 1 minus QR over 800 kilojoules per kilogram. Evaluate. Our QR is 141.2 kilojoules per kilogram. The next is at point 4. So we start at point 4. We have T3 is equals to T4. Then T4 is equals to 300 Kelvin. Now, RK is equals to 5.154, right? So, at P4, we have P3 V3 is equals to P4 V4. Then, V3 over V4 is equals to P4 over P3. We all remember that RK is equals to V3 over V4 and P4 over P3 is equals to V3 over V4. So, we can assume that RK is also equals to P4 over P3. So, let's draw a line right there. Then, RK is equals to P4 over P3. Then, substitute or arrange the equation. P4 is equals to RK times P3. Substitute the terms. P4 is equals to 5.154 times quantity 200 kilopascal. Now, P4 is equals to 1030.8 kilopascal. Now, we have T4 and P4. The missing now is B4. P4B4 is equals to RT4. 1030.8 quantity times B4 is equals to 0.287 kilojoules per kilogram per Kelvin multiplied by 300 Kelvin. Now, evaluate for B4. B4 is equals to 0.08353 cubic meter over kilogram or per kilogram since it's specific, right? Specific volume is B4. Now, we have 0.3, reverse, right? P3 is equals to 200 kilopascal. T3 is equals to 300 Kelvin. So, the missing one is the V3. For V3, we're going to use RK is equals to V3 over V4. Since we have RK and we have V4, we can say that V3 is equals to RK V4, right? Substitute. V3 is equals to 0.08353 cubic meter per kilogram multiplied to 5.154. The answer is 0.4305 cubic meter per kilogram. Can you follow? Can you still follow? If not, you can always go back and repeat it again. Okay? Practice and practice and practice until you made it. Now, at point 1, we have T1 is equals to 1700 Kelvin. V4 is equals to V1, right? So, V1 is also equals to 0.08353 cubic meter per kilogram. Now, for P1, we have P1 over T1 is equals to P4 over T4. The formula, right? Then, P1 is equals to T1 P4 over T4. Arrange it. Substitute. P1 is equals to 1030.8 kilopascal multiplied to 1700 Kelvin, over 300 Kelvin. P1 will now be 5841.2 kilopascal or 5841.2 kilopascal. Now, we have the last point, which is point 2. T1 is equals to T2 and T2 is equals to 1700 Kelvin, right? B2 is equals to V3 and V3 will be equals to 0.4305 cubic meter per kilogram. Now, we only have P2 to get or P2 to find. So, P1 V1 is equals to P2 V2. We have P1, we have V1, we have V2. The only missing is P2. So, arrange the equation. P2 is equals to P1 V1 over V2. Then, substitute 841.2 kilopascal times 0.08353 cubic meter per kilogram over 0.4305 cubic meter per kilogram. Evaluate using your scientific calculator, whatever way you want. The answer will be 1135.37 kilopascal. That will be our P2. So it seems that we all got the cycle points, right? So we go for the network cycle. W net is equals to QA minus QR. W net is equals to 800 kilojoules per kilogram minus 141.2 kilojoules per kilogram. Now, evaluate. Your W net will be 658.8 kilojoules per kilogram. Now, for the MEP, or the last one, the mean effective pressure will be MEP is equals to W net over VD. VD, or the volume displacement, is just the maximum volume minus the minimum volume. So, MEP is equals to W net over Vmax over Vmin. Our Vmax will be, our Vmax will be 0.4305 and our Vmin will be 0.08353. So, substitute, and our MVP will be 1898.72 kilopascal. Sorry for the shortcut. Now, that's the end of our example problem. So, my last tip for you is that you don't need specifically to follow the order of the solving, like point 1, then point 2, after the cycle points you head for the cycle performances, and last MEP. No, it always depends on the given, so analyze the problem carefully. And always remember, the diagram. Always draw it up before answering questions like this to prevent confusion. No? It's always the key to understanding thermodynamic cycles more in depth, or more proficiently. So we have a exercise problem here, so answer it by yourself. An ideal Stirling engine using helium as the working fluid operates between temperatures limits of 300 Kelvin and 2000 Kelvin, and the pressure limits of 150 kilopascal and 3 megapascal. Assuming the mass of the helium used in the cycle is 0.12 kilograms, determine the cycle, or the thermal efficiency of the cycle, or the EC. So I will put the answers here. I hope you evaluate this one. Answer is EC is equals to 0.85 or 85%. Did you get it right? I hope you get it right. So, that's it for today's discussion. I hope you learned something new about the Stirling cycle. Don't forget to like and subscribe for more video tutorials. Thank you for watching!